Hello everyone, my name is Rouqaiah H Al-Refai and I am here to present our paper, a unified model for face matching and presentation attack detection using an ensemble of vision transformer features, which is supervised by Dr. Karthik Nandakumar. Face matching and face presentation attack detection are two parts of a face recognition system. A face recognition system starts with a user who is present in front of a sensor where there is a potential of presenting a presentation attack artifact to fool the system. Whether it's a genuine user or a presentation attack artifact, a face detector detects the existence of faces in images or videos, and then key points, landmarks, will be identified in the detected faces to align them before matching. After that, the face region is cropped and declassified by presentation attack detection system into a fake image that will be discarded, or a real face that will go through the face matching module to verify the identity of the user. All these parts are summarized to three modules: face detection and alignment, face presentation attack detection, and face representation and matching. Face representation and matching schemes have evolved over the years, from the use of holistic methods, handcrafted features, and local descriptors, to the use of deep learning-based models, such as DNNs and vision transformers. Most of the early methods addressed one aspect of the unconstrained face challenges. They typically couldn't handle large intra-user variations in pose, expression, illumination, and aging. Several techniques have been also proposed for face presentation attack detection. Most of these methods exploit the fact that presentation attack instruments can cause image quality degradation during recapture. Feature-based approaches are classified into texture-based features and dynamic features, such as motion and vital signals. Deep learning, especially CNN-based methods, have shown good detection performance on various face presentation attack detection benchmarks. The motivation of our work, as we have seen, all of the three key tasks in a face recognition system, face detection and alignment, face representation and matching, and face presentation attack detection, are usually considered as standalone problems. Despite the recent advancements, the problem of designing a deep learning model that can jointly perform matching and presentation attack detection has been lightly addressed in the biometric literature, and only few efforts were made to combine multiple modules in a biometric system within one framework. One work has done it with the face and another with fingerprint. Both follow the naive approach of using a shared CNN backbone for feature extraction and dual heads for matching and presentation attack detection. We also can see that vision transformer models have been successfully adopted in the domain of image processing, and they have received significant research interest due to their generic nature and applicability for various computer vision tasks, including face recognition. The overall objective of this work is to design a multitask VIT model that achieves high accuracy for both face representation and matching and face presentation attack detection. To achieve this goal, we start with a vanilla VIT model. The VIT model splits an image X into a series of non-overlapping patches N, and flatten each patch into a vector using a linear projection layer. Then add a one-dimensional positional embeddings to retain the spatial information of the patches, in addition to a special learnable token that is added to the sequence before passing it to the VIT encoder network. A single VIT encoder includes three main elements: layer norm, multi-head self-attention, block, and multi-layer perceptron. In addition, residual connections are applied after every block throughout the encoder input to throughout the encoder. Input to the first VIT block can be denoted as, where the first N components represent the patch tokens and the last component, Z-note, denotes the class token. The essential part of the VIT encoders is the multi-head self-attention block that decomposes the attention in multiple heads to run the self-attention mechanism several times in parallel and learn the local and global dependencies in images. Self-attention learns the relationship between the patches using this equation, where Q, K, and V are the resulted vectors from multiplying the input Z with weight matrices of each one of them. The output representations of the Lth layer is denoted as ZL, as in the paper. The class token output of the last block is considered as the final embedding of the given input image. VITs have been employed for jointly performing multiple tasks. Bahat-Cherjee and others proposed a single end-to-end transformer framework to jointly learn multiple vision tasks. And the concept of self-ensembling of different levels of features was used to improve the transferability of adversarial attacks against VIT models. Finally, a cross-layer relation-aware attention and hierarchical feature fusion were employed to achieve good generalization performance on the face presentation attack detection task using VIT. Inspired by how VITs were utilized to jointly perform multiple tasks, we use the vanilla transformer as a backbone and evaluates two different architectures. The first one is a dual head model for the two tasks. The VIT backbone is fixed and acts as a shared feature extractor. On top of this backbone, two task-specific classifier heads denoted as H and J are added for each task. The class token embedding ZL obtained from the last VIT block is passed on to both classification heads. For presentation attack detection, it predicts whether the presented input image is bona fide or attack, where this head is trained with the binary cross entropy loss. And similarly, for the other head, it predicts the identity of the person. And this head is trained using the L face representation matching loss. Typically, VITs rely only on the class token at the last block for image classification, and it ignores the rest of the learned features, which are the intermediate class and patch tokens. Our hypothesis is that learning global face information is critical for the face representation and matching task, while microtexture features are important for the face presentation attack detection task. Attempting to distill both of these types of information into the same class token is likely to lead to suboptimal performance for one of the tasks. We propose a simpler alternative based on the insight that microfeature required for the presentation attack detection task are captured by the patch tokens, where the features extracted from these patch tokens can be used for the presentation attack detection task, while the VIT class token focuses on the face representation and matching task. As can be seen in the figure, classification branch is appended to each intermediate block of the VIT. This classifier takes the patch tokens generated by the block as input and outputs a binary classification decision, which can be a 0 or a 1. Two network architectures have been considered for the classification branch. The first one is a multi-layer perceptron that involves the 3 fully connected layers with ReLU activation function after the first 2 layers and sigmoid activation at the output layer. The second one is styled based on a CNN which composed of 2 convolutional layers with ReLU activation and max pooling operations and 2 fully connected layers for final prediction. The classification branch is trained by first fine-tuning the VIT backbone with face representation head using the loss for face representation and matching. Next, the backbone will be frozen and the patch representation extracted from the intermediate layer, and only the branch classifier will be trained using the loss for the face presentation attack detection. We have to keep in mind that the independent datasets are used for learning the 2 tasks. We append the face presentation attack detection classifiers to more than one intermediate block in the VIT and diffuse their outputs to obtain the final prediction. As for the dataset that has been used, Casio face dataset and labeled faces in the wild dataset were used to evaluate the face recognition task. Both datasets were pre-processed by detecting faces using MTCNN, then cropping the face region and resizing the images to 224 by 224. While the spoof in the wild dataset and the high-quality wide multi-channel dataset were used to evaluate the face presentation attack detection task. A special note to make about the SIW dataset is that it has been used for joint training of the 2 tasks, so the frame selection process has to be compatible with both task requirements. Therefore, we don't follow any of the 3 protocols specified for this dataset. Implementation details. For the backbone architecture, we use the VIT base 16 by 16 patch size, ImageNet 21,000 classes pre-trained. For face representation and matching, SGD optimizer with a learning rate 1E-3, and for the face presentation attack detection, an ADAM optimizer with a learning rate 1E-4. For the feature ensemble and the classification heads, we implemented 12 separate classifiers, one after each VIT block. The VIT backbone is fixed. An ADAM optimizer is used with 1E-5. and the task-specific classification heads updated with Adam Optimizer with a learning rate 1E-3. This table, the first one, shows a comparison of the face matching accuracy of the VIT model for the zero-shot face representation and matching scenario with ImageNet pre-trained VIT as feature extractor. So zero-shot means the backbone is treated as a feature extractor, and for the case when the whole model is fine-tuned using the large-scale Cassia dataset. We can see from the results that fine-tuning the VIT on a large-scale face dataset is clearly beneficial, leading to more than 10% improvement in the matching accuracy compared to the zero-shot case. We can also see that the fine-tuned VIT compared to the face transformer model proposed in the face transformer paper shows that starting with the ImageNet initialized weights and fine-tuning the model is a better option than training the VIT from scratch. As for the other table, the face presentation attack detection performance of the VIT is also enhanced by fine-tuning on the face presentation attack detection task. Here, when we train it on the SIW dataset, the fine-tuned VIT model achieves a lower ACR compared to the zero-shot scenario. As can be observed from this table, none of the dual-head models achieves good accuracy on both of the tasks. The second and third rows shows the results of fine-tuning a pre-trained VIT for one task and then fixing the backbone and training only the classification head on the new task, where we can conclude that features learned for the face presentation attack detection task are not representative enough to perform face matching, and the representations extracted for the face matching are insufficient to differentiate between real and attack images. Both joint fine-tuning methods fail to achieve good accuracy for both tasks because of the small size of the SIW training, which is only 72 identities. Since the dual-head architecture is infeasible, we see that the best result achieved with the feature ensemble method. From this table, we observe that the face presentation attack detection performance of the initial and mid VIT blocks are better in comparison to the face presentation attack detection head, which is based on the class token embedding. This demonstrates that the microtexture features required for the face presentation attack detection task are well represented in the initial and mid VIT blocks, in particular blocks 4 and 5, that provide the best accuracy despite the classifier type and the training strategy. We come back to this table to show that based on these results, we averaged the outputs produced by the 4th and 5th VIT blocks to build an ensemble classifier for the face presentation attack detection task. The performance of this feature ensemble VIT that we showed previously, the architecture, achieves a high face presentation attack detection accuracy of 99.12 and ACER of 0.91%. based on the MLP architecture and the face representation and matching fine-tuning strategy. We also evaluate the face presentation attack detection performance of the feature ensemble VIT under the unseen attack setting in the HQW MCA dataset. The performance results summarized in the table show that the proposed approach with face representation and matching fine-tuning outperforms the state-of-the-art results in the work in the second column. So for some attacks, like in the case of flexible mask, paper mask, and tattoo, while it outperforms it in these attacks, while it fails on other attacks such as glasses and makeup. While we are still investigating the reasons for this failure, we think that a potential overfitting issues are caused due to smaller sample sizes. However, it must be emphasized that our proposed method is fine-tuned for the face representation matching task, whereas the work that we are comparing to focuses only on the face presentation attack detection task. Without the face representation and matching fine-tuning, the proposed approach achieves better results for most attacks except glasses. In conclusion, we proposed using a feature ensemble approach to jointly learn both of the tasks. We exploit the architecture of vision transformer models to make use of local features extracted from intermediate VIT blocks to perform face presentation attack detection, and the global features learned by the class token to perform face matching. Experiments results proved that the VIT feature ensemble can achieve good performance for both of the tasks in comparison to our basic multi-head approach. And going forward, we aim to achieve a single VIT model that can implement a complete face recognition pipeline. Thank you.